Now, let's go beyond those and talk about some more generic non-convex solvers. We can have several generic solvers. I'm just listing 2 of them here, or 3 or 4, but there are much more than that. And then you can find some of them in food for thought. So the first one is successive approximation. What it does, it says that I know that probably my optimization landscape or the function is non-convex. I'm just going to get to some points. Around that point, I don't know how to optimize the whole function, but I know that how to optimize a good approximation of that function. For example, if around this point I tell you that this is your approximation, then instead of solving this function, you're going to approximate this function with another function like that. So just assume that the whole function is like this everywhere. This is just assumption, approximation. And then try to find the minimizer of this guy. So the minimizer is WK plus 1. Now try, in the next step, I can just depict it, I guess. In the next step, you're going to again do another round of this approximation. So that's why it's called successive approximation. So first you approximate this guy, then the optimizer is here. Now at this point, you're going to go for another round of approximation, second order approximation, for instance, and then you will find this guy, and then you get closer and closer to the optimal solution under some conditions. Okay, so this is called successive approximation. If you go with the second order approximation, you will find something like that. Doesn't have to be always upper bound of the function. It could be lower bound or whatever. And this is a first order approximation, and then try to minimize that within your bound. The first order called successive linear approximation, second order quadratic approximation. So again, you are not minimizing f, but you are minimizing a surrogate function, f tilde. And f tilde is like this one or that one, depending on first order, second order, or any other approximation that you are happy to use. Okay? Under some conditions, you can converge. What does it mean? It means that if you run that sequence of approximations, you will converge. And just to recall you can go back to slide 225 of lecture 2 and see that the actual gradient descent, they are actually running a sequence of this approximation. So this is exactly what gradient descent does. You can just show that. So at every iteration of gradient descent, WK plus 1 is WK minus 1 over L, G in this case, of gradient of f around WK. This is exactly like saying WK plus 1 is arc mean of f tilde around WK, and this guy is an upper bound of the actual function around that specific point. In particular, this is a proximal upper bound of this. You will see the definition of proximal later in the next slides, but then you have seen that in lecture 2 as well. So I'm just saying that even if the function is convex, you may somehow use these things unintentionally anyway. Question?
Actually, how do we approximate? I mean, in which range? For example, here, if I just change the range of x here, for example, or w, then the function that I approximate is different. I mean, how do we specify this?
So the question is, we want to approximate. In this case, we went for second order approximation, Taylor series. Usually this is the way to go, the easiest way to go. You will say that, okay, if I want to first order approximation, cut the Taylor series after 2 terms. If you want the second order approximation, quadratic approximation, then cut it after the second order, okay? And then you can have cubic approximation and all those sort of things. But then the question is, now once we do have a low order Taylor approximation, order 1, 2, 3, 4, definitely we cannot trust that, right? What we can say only is that we can trust this approximation within some bound on the input, exactly what you said. And that is the whole idea of trust region. So what it says that we don't optimize f here. So the solution is not argmean of f. We're going to constrain that within a bound, within a range over which we trust that. This is called trust region, actually. And then you will see that in food for thought. So there is a whole branch of algorithms within the name of trust region, which is pretty popular in optimizing convex non-convex. Yes, it essentially says that I'm trusting this region, I'm trusting this low order approximation of Taylor's within this bound. So whatever the solution within this bound, I'm happy with that because I'm trusting that. And then all those there are lots of clever ideas to say that that bound should grow to 0 and 0 and 0, meaning that we can increase and increase and increase our trust to that upper bound. And then once we find the solution to that upper bound, then we are done, okay? So this is the whole idea. But then trust region is usually for quadratic upper bound. Then there are some cubic upper bounds as well. And then the whole idea of how we can trust them as well. Okay, cool. So the whole idea of successive approximation is we don't know the surface of the function everywhere, but we know a surface of the function around the vicinity of this point, approximated by first order, second order, third order, and then we just try to optimize over that approximation around that point. So this is the whole idea of successive approximation. Under some very mild condition, you can converge to again to a stationary point. Okay. The second kind of algorithm is completely different philosophy. So in this kind of algorithms, generally they are like called alternating optimization or coordinate descent, block coordinate descent, and lots of other names. But what they essentially say, well, one of them is, let's say I'm giving you a matrix factorization problem, which is minimize xy minus a to power 2 over x and y. You might have some constraints on x and y, but then there is a non-convex optimization in general. How we can solve this? Well, one of the easiest things that you can imagine, well, you can say that, okay, I'm just fixing x, and now I'm having a quadratic optimization, and then I'm just finding y, okay? So I'm just saying that in that case, y is equal to argmean of over y of x, y minus a. So now consider that this x here is not a decision variable anymore, it's just a constant matrix here. And then you can find over y, and then call this y of k, and then go for it with x. Now you have find the optimal a, the optimal y. So now try to find the same thing for x as well. Just fix this guy and then find the optimal one for this guy, right? Then say that x of k is argmean of x, y minus a. But then here you have this choice of saying, okay, I have solved that for y, so I know a new y. Why not just plug it in this y instead of all the previous y or some random y or whatever, right? So why not plug it in? So this is a very natural choice, and this is called actually coordinate descent. Well, in that case, it's block coordinate descent, because at every iteration you are solving over a block of coordinates. A block of coordinates means that if this is n by n matrix, so you're solving over n2 block of coordinates for this guy in this, and here you're solving over x, another n2 block of coordinates, okay? So that's why it's called coordinate descent. You're gonna, with some rules, and those rules usually they don't have to be really smart. With some rules, you're gonna pick some coordinates, find the optimal solution with respect only to those coordinates, and then iterate. So here, if this is the sublevel sets, then we're gonna start with some x1, 0 and x2, 0. Just imagine here, let me, I'm not sure if I can write something down there. Okay. I'm trying to put something. Okay. I could. So imagine that this is the gradient at that point, and gradient descent says that we should go toward here, minus of the gradient. But coordinate descent says that we really don't need to go that way. This is the direction that we should go, but then we just go to one of these coordinates. So this is this coordinate and that coordinate of that vector. Just pick randomly, for instance, one of the coordinates and then update with that coordinate. So this is the whole idea here. Seems very simple. But then actually you can really converge. And then the convergence is pretty fast. So you can have many update rules, like cyclic update rules, which essentially says that start from the first set of coordinates, go to the second, third, all the way to the end, and then again go to the first one. And then do these kind of round robin iterations to converge. And then you can show that if there are some conditions like individual coordinates, they are LG smooth, then you can have a convergence of this rate. And if they happens to be also mu strongly convex, then you can have a linear convergence rate as well, which, by the way, scales with D. Okay, and then we can have this form of convergence, pretty good. But then the thing is that for most of these things to work, we need to have a smoothness of the function. We need to have a smoothness of the function, and in some cases, convexity, not in general. This function is not convex, but convexity with respect to the coordinates. So here, if we fix this guy, this is convex, and if we fix that guy, then this is another convex function. So we have convexity with respect to coordinates, but we don't have joint convexity. But then if we do have such scenario like that, then we can ensure this convergence rate. But then in the next slide, we will see what would happen if we don't have them. So if we don't have a smoothness or convexity with respect to individual coordinates. Question?
How do we select, these coordinates? Because I think it can affect the rate of convergence. Doesn't matter that which one you choose, or, if we choose it randomly.
So the question is, if we do have, let's say, this optimization, how you choose coordinate. In this case, y you should choose x as a set of coordinates and y as another set of coordinates. Y I shouldn't choose, let's say, x. I'm just writing down as x1, x2, okay? And y as y1, y2. I can do that. I can write it down. And now, instead of optimizing over x and y, I do have optimization over x1, x2, y1, y2. Over 4 variables. I can do that. And then you can easily show that with respect to individual of them, once you fix everything else, again, you have another form of convex optimization with different y and different a. Well, a is the same, but essentially some terms will be adding up here based on this product here. But then you can do that. So it really, the question of how to select those coordinates, in the worst case, you can select one coordinate as one decision variable. So if you have a neural network with 1,000,000 decision variables, then you have 1,000,000 coordinates. But then the thing is that if that neural network happens to be 10 layers, then you can say that all these W's, of course, it depends on the structure of the problem. But then if you can show that with respect to all the weights of one layer, so it's n by m very big matrix, if it is convex with respect to all those coordinates, then you can just define that as a block of coordinate. Exactly like what I did here with respect to the block of coordinates like x. So there is no unique answer, really depends on the question. But as long as you can preserve convexity with respect to those block of coordinates, then that's fine. You can just define one set of variables there. Question?
So this convergence rate, is it probabilistic or whatever random coordinate you select, it will always be this convergence?
So the question is, here we said that there are lots of convergence, and then there's lots of update rules, iteration among those coordinates, and what do we need to have these convergence? Can we always converge? No, we cannot. So if there are some random coordinate selection, there should be some process, or let's say some assumptions on that random process. So for instance, we should be able to see that random process of coordinate selection should be such that we can see infinitely many times all the coordinates, okay? So we're gonna need some form of assumptions on that random process, but then those are usually easy to satisfy. So for instance, if we just uniformly at random pick coordinates, then we can converge. Something like that. Okay, so we ended up to scenario where if we do have, so first we have seen that if we really don't know anything about the function, the easiest thing that we can do is just approximate locally, solve that, and then it would be much better if that local approximation or your local approximation is convex or strongly convex. Why? Because if this is a strongly convex, then you know how to solve this. How you can solve this? Upper bound. You can run gradient descent on top of that, right? And then if this is a strongly convex, then you can linearly converge to the optimal solution here, right? So why you should choose a strongly convex? Can you do that? Yes, you can, because this is your approximation, right? So just make this approximation to make sure that this is strongly convex then you can find this guy very easily. Okay, so this is if you don't know anything, and then just successively do that. Here we do have another problem. So we split the problem here instead of the function itself on different coordinates. But then it works if the function behaves very well in every coordinate. But what would happen if it doesn't behave very good in some coordinates? So if we don't have a smoothness or strong convexity in some coordinates, we might still be able to converge, but then the convergence, we might not be happy with that. Then what we can do, why not combining the idea 1 and 2, right? Very simple one. So what it says that if it just happens that with respect to some coordinate, the function is like this, with respect to this specific coordinate j, for instance, then why not? So this is non-convex. Optimizing, finding the minimizer here could be hard. So why not just going for approximation here? And just make sure that just for some convergence analysis, make sure that the approximation that you want to have here is just upper bound of the function, always upper bound. Then it means that if with some coordinate, still we are running coordinate descent, so we're splitting the problem in different coordinates and then solving in the individual coordinates, okay? But in some coordinates, the function, it doesn't behave well. Then what we can do is that we can use the idea first, the first idea, and then try to find some upper bound here, a strongly convex upper bound usually. Again, this is our choice, so we can make it a strongly convex, we can make it a smooth. So why not doing that? So we will find this f tilde or ui here, and then find the optimal solution here. And just pick that point as the solution of that specific coordinate. Okay? So that is the difference. The difference again is that if we wanted to run the original coordinate descent, the function behaves like that. And in this iteration, you can see that we need to pick argmin. So we need to find the global minimizer of that function. And the global minimizer of this function, this is non-convex, so it could be pretty hard to find that. The global minimizer is just this point. But then we might not have efficient solvers to find this point. But what we can do is that we can find an approximate solution using the first idea, right? Upper bound, and then use this one. So it's just essentially combining the first two ideas. But then you can just converge here. But then what's the great thing about this idea is that now you can really split the problem in individual coordinates. And whenever you have some problems like smoothness of the problem, if you have a composite functions like g plus h, where h is non-smooth, so then you cannot define derivative. And then you cannot find this point, even you cannot run gradient descent. So what you can do is that, so therefore you cannot run this BCD things. Then what you can do is that you can go with a smooth upper bound that you're happy with and then run that. Or just run proximal method on that specific iteration, that specific coordinate, or run subgradient methods, or whatever you like. The thing is that now it's really splitting up to individual functions and individual coordinates, and then you can just use upper bounds or successive approximation there. So this is pretty much the whole idea. And then this is just proximal upper bound, which is the function plus a proximal addition here. And then you have seen that if you use this guy over the function around wk, then you can recover gradient descent iterations actually. And this is proximal iterations anyway. But then that gives a proximal upper bound. So this is exactly proximal upper bound around that function, around that point. And that's it. Okay, cool. So we have one main question. Can you run a stochastic gradient descent here? Or SVRG or whatever we have seen in the last lecture? Can you run them? Cool, why not, right? So you can run them. You will find some point at which gradient vanishes. This is the whole idea of gradient descent or stochastic gradient descent. You can run that. There is no other guarantee with BCD here. Just recall that here we are in this section. So finding a stationary point, all we are happy with is just finding a stationary point. Gradient descent can do that for us. A stochastic gradient descent can do that for us. The problem with gradient descent is the scalability. So that's why that we had in lecture 3 all the different versions of stochastic gradient descent. But we can run that, okay? Also we can run coordinate descent. That's true, yeah. Also, we can run coordinate descent, okay? So which algorithm we should choose? What do you think? Is it better to go with coordinate descent or stochastic gradient descent? Well, of course, many different versions of them as well. But what are the main differences between these two? So just to make it clear, let's put them side by side. Here in coordinate descent, we pick one random coordinate in the random selection and assume that this is uniformly at random, some coordinate. And then we do this update. Wk plus 1 is Wk minus alpha k gradient with respect to that specific coordinate of f. Okay? For that specific coordinate. So we do have all the gradients, but then we update only with respect to one specific coordinate, setting all other gradients to 0. So this is the whole idea here. Setting gradients means to 0 means that we don't have any update with respect to those gradients or those coordinates, but with respect to just one coordinate that has been selected here. In a stochastic gradient descent, on the other hand, just look at where I put this I here. Here it's with respect to some coordinate, whereas here is with respect to some functions. So you randomly pick one function, get all the gradients of that specific function. So again, this is an approximation of the gradients. The difference there is that in coordinate descent, you have 0 everywhere, but true value in some coordinate. In stochastic gradient descent, you have randomness everywhere, but then you have some value everywhere. It's not 0. Okay? And then you will update based on that random selection. Which of them you prefer, you think? If I just tell you that you are free to choose both of them, which of them you would go with? Why? Because I said that? Is it true? Less gradient computation? Because sometimes you cannot ask Oracle to give you one coordinate, the gradient with respect to one coordinate. Sometimes the only thing that you can say is that just give me one gradient. Of course, it depends on the structure and how you can obtain the gradients. But sometimes it's just that you can say how many gradients you want to find. And that's it. So just imagine, for instance, in a decentralized or distributed optimization where Fi, F1, and F2 is on different nodes. The only thing that you can say to that node, and the whole problem is from the communication, it's not from the computation, right? So you want to collect as few as possible than those coordinates because you don't want to communicate to those nodes and then ask them to send me back the gradients, okay? So in that case, the problem is not which coordinate you should access or try to reduce the number of coordinates. It just try to reduce the number of those gradients that you will ask from individuals. There are some scenarios like that, but then if you have a training of a neural network in a centralized fashion, then you can just ask that solver, that backpropagation, to give you the gradient with respect to coordinate of Wi, for instance. So in that case, you have a full control of. You have lower complexity if you limit yourself to one set of coordinates and then try to find the gradients with respect to those coordinates. So depending on the scenario, the complexities could be different. But then let's give this example here. Let's say this is W star, the point that we want to converge to, and I'm just drawing some random gradients here. So these are actually minus of the gradients, okay? Yes. So these are, again, minus of gradients. So this is gradient F1, gradient F2, gradient F3, again, minus, 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 and very small one, gradient of minus F4. Okay, so the same scenario here as well. And the combination of everything here, let's say that this is your final gradient here, and the same thing here. This is your final gradient. Okay. In coordinate descent, what happens is that it will randomly pick one of those coordinates. So in that case, assume that it's just 2-dimensional. So it either choose, this one is actually this, and this, right? So this is gradient 1 and gradient 2, and gradient of f is equal to gradient 1, gradient 2. So it randomly picked one of these coordinates, setting the other one to 0, and then updating that. And then assume that this is the optimal point that you want to converge to, okay? So what happens here is that we don't know, it's better to go toward W1 or W2. Well, we know anyway, but then the thing is that even if we go with random selection, so pretty much similar to SGD, then it just doesn't matter if you pick W1 or W2, right? you're going to have some progress toward the optimal solution, either this way or that way. You're going to have some progress. But what would happen here? We are not choosing coordinates. We are randomly choosing one of these vectors. So this is gradient 1, 2, 3, and 4. We are randomly choosing one of these gradients. If we are lucky enough to pick one of these, then we will go closer to the optimal solution. Again, this is minus of gradient. But what would happen if we randomly pick this guy? And of course, there is a chance that there are many more of these guys toward the negative half space that we want to go through. So in that case, we are not improving. So what it says that in every iteration, in a stochastic gradient, there is, so let me put them here. Okay, so in a stochastic gradient, there is no guarantee that in every iteration we can improve, whereas we do have this control, this robustness in coordinate descent. So that's a very great thing. And that's why that, for instance, if you want to run acceleration, then it's pretty hard to run acceleration on a stochastic gradient descent or vanilla stochastic gradient descent. So the momentum that you will get, the momentum says that try to use the previous information that you have. But then the previous information is kind of corrupted. Why? Because you have moved towards something which is not in the same direction anyway. So you shouldn't use the momentum that way. So that's why that there are lots of approaches that if you want to go with the stochastic gradient descent, then we need really some form of variance reduction techniques like SVRG that we have seen, or whatever that somehow stabilizes this estimation here. So that is the main idea here. So if you can somehow trust your gradient estimation with your definition of trust, then that's a great idea. And in some scenarios like distributed learning, or distributed optimization in general, then there are lots of benefits of using SGD. But then if for your specific case, there is from the convergence analysis or complexity in terms of communication or computation, there is not so much difference between these two, then you may go as well with coordinate descent due to the robustness. That was what I wanted to say here. Okay, cool. So here we have seen 3 different approaches, successive approximation, coordinate descent, and successive upper bound minimization, so combination of the first 2. And then you have seen that you can run, of course, gradient descent, stochastic gradient descent, and all those kind of things. Any questions so far?
In previous slides, I don't remember exactly slide, you said that we isolate our non-convex function to some convex pieces and then find the minimum for them. Actually, how do we split them? I mean, this is important that how we split, because if we split it in very small pieces, then we have many small pieces and we compute this for all of them. And so we use many power, computation power for that. However, we could just have one pieces and find the minimum, local minimum for that. I mean, I don't understand how do we choose these pieces.
So the question is, if I give you a function over the entire support, how you can divide that to individual portions subsets in that support, and then say that, okay, the function is convex here or there. First, for some algorithms like this one, we really don't need to have that. So here, what we do is that, first of all, we're not assuming that the function is convex anywhere. The only thing that we assume is that the function can be approximated around some points. And this approximation doesn't have to be convex. We don't have to have a convex approximation of that function. For example, if you go to the 3rd order Taylor series, or 4th order, it doesn't have to be convex in general, right? So the whole idea is that for this specific type of algorithms, you really don't split the whole support here. What you do is that you will start from W0, for instance, approximate the function around that W0 over some region that you can trust. So in that case, you can trust the W within this ball, this region here. I can trust whatever the function is within that region. Of course, you can just reduce that and reduce that to make sure that your approximation is valid, right? And then try to optimize over that. For example, if I want to say that this is the region over which I'm trusting, then this approximation would be like that. The approximation of this function would be like that within this bound. And then you will find this guy, which is the minimizer, map the back, and then here, again, you have another bound over which you can trust. Well, that should be symmetric usually. So now I'm trusting the approximation of the function around this point, around this bound, okay? So then you have another upper bound. It could be upper bound, doesn't have to, but just assume that this is an upper bound. Then you have another minimizer, and then you can do that successively to be finally you can find. But then you need to make sure that you are reducing the radius of that trust region to make sure that whenever you're closer and closer to the stationary point, the radius goes to 0. This is that. But then if there are some structures, somehow happens for you to know how to use that structure in your specific problem, then you can end up to a scenario like that, where you can say that for your specific problem, so this is your task actually, that for your specific problem, you need to show that there is a region like W, that the function is convex over there. And I need to do, my task is just to make sure that W0, sorry, is within this W. So I need to show that there is some W. Again, I don't need to say that the function is convex everywhere or it's convex here, 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 here. My task is just to find one of those W's and if I'm happy with that or not. It might be that for your specific function, you cannot find that. For example, assume that the function is like this. The same function, but then there are lots of high frequency noise over there. And this is actually something that you will see a lot in high dimensional optimization. The functions are something like that, very high frequency noises. Especially, just imagine that, we will see that actually later. I'm not sure if I would have time to go to that or not. But anyway, this is what happens with empirical risk. And this is your actual population risk or Bayesian risk. So this is the function which is very smooth. It doesn't have to be convex anyway, but definitely it's smooth. But then your empirical risk is Monte Carlo approximation. So what do we have? Recall that we have this guy, right? And this is somehow a Monte Carlo. That's the reverse. It's a Monte Carlo approximation of E of f, right? This function is a blue curve here, which usually very smooth, and this is not. Depending on the n, of course, but then if n is not large enough, then this is definitely not as smooth. There could be large of ripples like that. And it just doesn't matter. Just imagine that there is a ripple like that, and then you will find an optimizer that gives you this point, which is pretty nice. But then you will apply that to the test error, and then in the test you will say that, okay, it performs much worse than whatever I have seen so far. In the training, I had this point. This is some loss function, right? In training, I had this point. I was very happy with that. It was close to 0, but it's not in the test. Why? Because the point that you are exciting your function is actually here. And this is what you will see probably in the test. But it could be that since the test is another things like that with another n, which is n number of test samples, it could be that for test, it just happens that it's like this, if n is not large enough. Then it might be that you have in a training this error, and in a test you have this error, and then you will wonder what happened here. Nothing, it just n was not large enough, that's it. So in that case, even finding some region over which the function is convex, so in that case I'm just telling you magically that the function is convex over this region. And then you will find pretty easily with any solver this point. But are you happy with that? No. So there is another thing going on here in that scenario. But what I said is that if there is a structure and you can show that a structure, then you can run gradient descent. Being happy with the solution is completely another thing. Okay, cool. So far, whatever we said is just how to find a stationary point. Now let's talk about how to find a local minima. Essentially now we want to find a second order necessary point or approximate second order necessary point. So again, this is the definition of second order or approximate second order necessary point. The gradient should vanish. We know how to achieve that. We have seen a lot in the previous set of slides and lectures. But now on top of that, this is definition of stationarity. But then now on top of that, we want to have an almost PSD Hessian matrix. So how we can do that? This is a function, a convex function. This is a function where we do have this saddle point, and this is the gradient flow of this function here. So where the gradients goes, and then this point here just is consider that this is exactly that point. So can you imagine the gradient flow for, the gradient flow essentially says that this is the direction of the gradients, okay? And can you imagine that what is the gradients here? There is a sink, right? So everything, it just doesn't matter from which point you take the gradient. You will go to 0, downhill, and then go to 0. So all the directions should somehow point toward that sink here. But then here, there is a saddle point. Why? Because you can see that in some directions, you are moving toward that point. But so here in these directions, you are moving toward the center. But then in this direction, which is minus y squared, you are actually going out from this direction. So this is source node, so as to say. So in that case, we do have a saddle point here. But then if somehow I tell you magically these gradient flow, then you know how to escape this point, right? If you run gradient descent, then what happens is that in gradient descent, you will find this point. And you will get stuck at that point because the gradient vanishes. How you know that the gradient vanishes? The lengths of these guys are the value of the gradients. And then here you can see that the gradient is 0. Okay. So how we can escape this point? It's really easy. If I know that these points are, the gradients are here, and I know that if I just move toward that direction, I will somehow, this is a little bit too much to say that if I know that I'm going toward that direction, nobody knows that, okay? The system should be, the sequence that you are working with, it should be causal, so you don't know what would happen in future anyway. But if I tell you somehow from here that if you keep moving toward that direction, you will end up to some saddle point, you can from here start to move toward that direction, just to go toward the gradients that you have here, okay? And that's it. Or let's say not the gradient, toward the right direction. The right direction means some eigenvalues, okay? So you can just move toward that eigenvalues and then escape from that saddle point. So this is pretty much the whole idea here. But if I don't tell you that in future you will get stuck at that point, then you can just run gradient descent. Whenever you're stuck at that point, so this is the point that you will stuck, whenever the algorithm is stalled here, then just find the Hessian matrix. Hessian matrix tells you that if you move toward this direction, the function gonna be decreased. You will see, you have seen that in first lecture, I guess. Just write down the second order Taylor expansion, and then the last term, if you move toward those eigenvectors corresponding to negative eigenvalues, then you will go downhill. Okay, then you can do that. So here, go here, and from here, there, go there. Okay, but then clearly you can see that it would be much nicer if you can move right away from this point here. Okay. Anyway. So this is Hessian-based, if I tell you what is Hessian, but what if, so this is Hessian-based approaches. They are usually expensive because you need Hessian information, but then they can be very efficient in some cases if the complexity of finding Hessian and the complexity of finding gradient and the complexity of finding Hessian product vector is the same, because what you need usually is not the Hessian itself, it's Hessian vector product. So if the complexities are the same, which you can see in some cases like this, then this could be much more efficient than this anyway. Okay, so what is Hessian-free approaches? It essentially says that, and this is pretty nice results. So it's very simple perturb gradient descent. What would happen here if I do this update? WK plus 1 is WK minus this guy, which is vanishes anyway, because now we are close to the stationary point. So this is vanishes plus some noise. I'm just randomly adding some noise sometime, not always. What would happen? I just added some noise. So it happens that if the noise is somewhere here, then I'm running that again, and I'm again converging to that point. But if just by random, this noise happens to move that W towards somewhere here, then we escape saddle point, right? Very easy. And then actually you can show that with this, running this, whenever this satisfies, so first order stationarity satisfies, so you think that you are close to the minimal or local minima, then run this. Otherwise, don't run that. It's a very simple algorithm like that called perturb gradient descent. So again, you have normal gradient descent, and you will add some noise whenever the first condition satisfied, something like that. And then you do that 3 times, 4 times, 5, so something like that. And then you can show that you can really escape saddle point extremely efficiently. And extremely efficiently means that the number of times addition that you need to run, so if the problem doesn't have any saddle point, you have some convergence. If the problem happens to have saddle point, then you need log d. D is the number of parameters. So you need a log d penalty to be able to escape that saddle point. And so this is a log dependency on d, so almost nothing, right? You can, of course, run SGD, and that's pretty nice because in SGD, stochastic gradient descent, this noise comes for free in all the iterations, right? Because you don't have the gradient, you have gradient plus some noise, and gradient plus some noise multiplied by alpha. As long as alpha doesn't decrease to 0, then you have alpha multiplied by that noise, so another noise. So it comes for free for you. And that's why this is pretty nice for escaping saddle points as well. Okay, so no wonder why in training neural network with some versions of a stochastic gradient descent, why you don't stuck at saddle point. Simply because you cannot stuck at saddle point usually. Okay, cool. So this is a generic Hessian-based algorithm. I tell you now what is perturb gradient descent. Pretty much similar to this. You just need to change a step 2 and a step 3. That's it, and add a perturbation. But this is Hessian-based approach essentially says that whenever gradient is not vanishing, so it's larger than your tolerance ball epsilon g, then run a normal gradient descent with a step size LG. So WK plus 1, WK minus 1 over LG gradient of f with respect to WK. That's it. Just run normal gradient descent iterations. Whenever this doesn't happen, then it means that we are in the region where the gradient is very small, so almost vanishing. So in that case, check the Hessian, the minimum eigenvalue of the Hessian, and if it is not larger than epsilon h, so if it is not sufficiently PSD, positive semi-definite, then it means that now we are in saddle point. What would happen if this doesn't satisfy and that doesn't satisfy? It means that we are in a ball over which gradient is almost vanished, and the minimum eigenvalue is sufficiently close to 0. So then we say that this is by our definition approximate second order necessary point. So then terminate. But then if we are not there, then just find the minimum eigenvalue like this. So solve this optimization problem here. Find this optimization problem here, find a vector that we do have this for lambda mean, which is the minimum eigenvalue, find the corresponding eigenvector, and do this update. And this update is just nothing but saying that WK plus 1 is WK plus enough magnitude to be able to make sure that now we are going out to the saddle point. That's it. And enough magnitude, you just need something in that order. Just for sake of proof. So essentially it says that go toward the right direction, W. The right direction is the direction toward W mean, lambda mean. So the strongest negative eigenvalue, and then give a little bit of momentum to that to make sure that you're escaping saddle point. So one question, is it really important to go toward the minimum eigenvalue? Just imagine that there are 2 negative eigenvalue and then they are pretty much similar. It really doesn't matter if you go toward the most negative one, as long as it's strong enough. It means that strong enough means that you will somehow go out of saddle point, and then you can make it sure, make sure by playing with this guy here. So just find some negative eigenvalue. It should be sufficiently strong anyway, and then go toward downhill with that direction. That's it. And then you can show that the number of iteration in that case gonna be like this. So this is your initial guess. This is the best things that you can go to. And you need the number of iterations in that order. I had a proof, but then proof is just 4 or 5 lines, is nothing. So you will say that at iteration k, either I'm reducing the function by this, which you already know how much you can reduce. It's a linear factor. Or you can reduce the function by this. And in that case, you have this bound. So either in every iteration, you have a reduction like that or reduction like that. So the number of iterations that you're going to need to achieve any desired bound is just minimum of these two. Then you'll be happy. That's it. I guess that we can skip the last one. So here, the essentially says that we really don't need to go to the highest reductions. So the lowest eigenvalue, as long as it's negative, then that's fine. Should be sufficiently large, though. So some food for thought. This is the things that you have asked about trust region, and then you can recover cubic regularization introduced by Nestrov in 2006, which pretty much similar to that. Instead of having second order upper bound, you have a third order approximation upper bound based on, this is called cubic regularization. And that's it. The second item is Lanchow's algorithm, very, very important one. Essentially says that how you can solve this optimization problem, how we can find lambda mean in an efficient way. This is called Lanchow's algorithm, usually. Okay, and then see the first one as well. Also regarding, I just wanted, you can find some examples in special cases here. This is what I said. So here you have expectation or population risk and empirical risk, and then you can go to this reference to see how we can smoothen these things using Gaussian smoothing. Okay, great, thanks.